In this first example, Sam put $10,000 into a certificate of deposit with a fixed interest rate for 5 years. And the table shows the value of the CD as a function of time. So initially it was $10,000 when he first put the money in, and then after a year it was 10,200, and then 10,404, and so on. So the first thing we are asked to look at is the average rate of change and the relative rate of change over each interval below. So let's first of all look at the average rate of change. All right, so average rate of change, you're taking the change in the function over the change in the independent variable. In this case, that's time, right? So we're going to find the dollars per year that the CD increases each year. So in this case, because the years are going up by 1, right, each time, we can look at the difference between these two. So if you look at the difference between these two values, you get, it looks like it increased by $200, right? So that's an increase of $200 over 1 year. So 200 over 1 then is just 200, right? So the first average rate of change here is just 200, right? It increased by $200 in the first year. And then let's keep going. Let's look at the next year. It looks like we added $204, right? Over 1 year, so the average rate of change is 204. And so on, right? I'm just going to look at the difference in the value of the CD over the difference in time, which is always a year. So let's see, I got this next one, I got to be 208.08, 212.24, and then finally, let me scroll down just a touch here. The last interval from 4 to 5, I got a difference of 216.49 over 1 year. So that's an average rate of change of $216.49 per year in that last year. Okay. All right. So it also asks us to look at the relative rate of change. So remember, when we find the relative rate of change, let me just remind you, since that's been a little while, relative rate of change, right? We take the second quantity minus the first quantity and divide it by the first quantity, right? So we're looking at the difference in the two quantities over the interval, right? Taking the second minus the first and then dividing by the first. So we're looking at how the amount changed relative to what it was initially. So let's just do that for these. Now the quantity, right? The quantity, like for this first interval, we're looking at the interval from 0 to 1. So over the first year, the quantity is the value, right? So in this case, we're looking at, let's say that this is a function. Let's call this v of t. So we're going to take v at 1 minus v at 0 and divide by the value at 0. Okay, for that first one. So we're basically going to take the change is $200. We have all the changes calculated here in the average rate of change because the time interval was just 1 unit. All of these are just the difference in the quantities in the values of the CD. So, but instead of dividing it by the time interval, we're going to divide it by the initial value. So we're going to take 200 and divide it by 10,000. So right, this is going to the change here is 200, and we're going to divide it by 10,000 for this first interval. So what we get is 0.02. Okay, and then the next interval, we're going to look at the value at 2 minus the value at 1, which is 204, and we're going to divide that difference, 204, by 10,200. And if you do that, you also get 0.02. And if you do that in each case, you get 0.02. 0.02. So that's interesting. We have a constant relative rate of change. All right. So let's scroll down here a touch and see what other questions they're asking us. What can you say about the concavity of this function? All right. Well, so if you remember, concavity relates to how the average rate of change is changing, right? So in this case, the average rate of change is increasing, so the function is concave up. All right, so the value of the function is increasing, right? Because the amount of money is growing in this account. And also the average rate of change is increasing. So if you were to sketch this, it would look like an increasing concave up function, sort of like that. All right, let's look at the next one. Interpret the relative rate of change of this function. Well, you can see it's constant, right? It's constant. Now, if you now we're gonna learn more about interest rates and things like that later on in this chapter. But if you look at this, is the the problem said that this CD had a fixed interest rate. All right, so actually that relative rate of change is the interest rate. It's the percent increase in the percent increase of the value each year, and so that means it is the interest rate for this CD. All right, so like I said, we're going to learn more about interest rates and things like that at the end of this chapter. So the last question asks us to write a function v of t for the value of the CD over t years. Okay, now this is a little bit more challenging, but let's think this through, right? So let's actually look at, we know this thing has a constant relative rate of change. Okay, so the relative rate of change is constant. So let me just look at this first year a little more abstractly. Okay, so the relative rate of change, we found that v1 minus v at 0 over v at 0 was equal to 0.02. Okay, now I can rearrange that into a formula for v1 given v0 if I just isolate v1. So to do that, I'm just going to take, I'm going to multiply both sides. I'm going to multiply both sides by the value at 0, right? V at 0. So then what I end up, these will cancel, and then I'll have v1, well, let me write it the way in function notation, minus v at 0 equals 0.02 v at 0. All right, and then I can isolate v1. So v1 is equal to, I can write it as v at 0 plus 0.02 v at 0. So you can see we're taking the value of the function at time 0, and we're adding 2% of it, right? 0.02 times v0 would be 2% of v0. And so now we can also write this, I got a common factor of v0, so I can actually write this as v0 times 1 plus 0.02, right? Or I could even write this 1 plus 0.02 as 1.02, right? It's one single number. So v1 is just going to be v0, and then we're multiplying v0 by 1.02. Okay, so v1, I'll just go ahead and write that. V at 0 times 1.02. Right, we're just multiplying by a constant. Now when I want v2, right, I want v2, v2, I can do the same thing as I did up here. I can rearrange it, and I can find that v2 is equal to v1 times 1.02. Okay, but I can substitute v1 with the expression I've got here and put that in for v1. So v2 is equal to v at 0 times 1.02, because that is v at time t equals 1, and then that's times 1.02. So you can see I basically get, let's see, v at 0 times 1.02 squared. All right, And I can keep doing that. I can say, okay, V3 is going to be V at 2 times 1.02, but then I can substitute this expression for V2. So what we end up with is we end up with V at T is equal to V at 0 times 1.02 to the T, right? Because we're just multiplying by 1.02 every time, right? We're adding 2% of the previous amount every time. So we're taking 1.02 times 1.02 times 1.02 T times and multiplying that times the initial value to get the value at time T. So, but we know what V0 is. Okay, so I should probably replace that. So V at T is equal to 10,000, right? And so 1.02 to the T. Okay, and you can check that out. You can put in some values of T and make sure that that function gives you the values you have in the table, right? So when T equals 1, 10,000 times 1.02 should be 10,200. And when T equals 2, if I take 10,000 times 1.02 squared, I should get the 10,404. Okay, so now we have an expression for the value of the CD at any point in time. All right. So you may have noticed that this is a case where we don't have a constant average rate of change, but we do have a constant relative rate of change. And that's what we're going to be talking about in this chapter is functions with a constant relative rate of change over a fixed time period, right? So when we talked about linear functions, when we talked about linear functions, we saw that they had a constant average rate of change. And these new functions, which turn out to be exponential functions, you see that this is an exponential function because the variable is in the exponent. So that's why we call it an exponential function. Okay, that means that the variable, right, or and I should probably say the independent variable is in the exponent. Right, that's what an exponential function is. So that's what we're going to be talking about in this chapter. So I will meet you in the next video for another example.